Hello, and welcome. In this video, we will explore key concepts in polynomial algebra that are fundamental to the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to: first, apply the remainder theorem to find the remainder of polynomial division without performing the division itself. Second, use the factor theorem to identify factors of a polynomial and solve for unknown coefficients. Third, understand and apply the fundamental theorem of algebra and its properties, especially the conjugate root theorem, to find all zeros of a polynomial. Let's begin with the remainder theorem. Our first objective is to apply the remainder theorem. This theorem provides a shortcut for finding the remainder of a polynomial division. The remainder theorem states that when a polynomial p of x is divided by a linear factor x minus k, the remainder is simply p of k. Let's understand why this is true. We can use the division algorithm, which states that for any polynomial p of x and a divisor d of x, we can write p of x equals q of x times d of x plus r of x, where q is the quotient and r is the remainder. In our case, the divisor d of x is x minus k. So the equation becomes p of x equals q of x times the quantity x minus k plus r of x. A key property of polynomial division is that the degree of the remainder must be less than the degree of the divisor. Since our divisor, x minus k, is a linear polynomial of degree 1, our remainder, r of x, must be a polynomial of degree 0. This means r of x is just a constant, which we'll call r. So our equation simplifies to p of x equals q of x times x minus k, plus the constant r. Now let's substitute x equals k into this equation. We get p of k equals q of k times the quantity k minus k plus r. Since k minus k is 0, the entire first term, q of k times 0, becomes 0. This leaves us with p of k equals r. This proves the theorem. The remainder is equal to the polynomial evaluated at k. Let's see this in action with an example. We will find the remainder when x to the power of 4 minus 3, x cubed plus x minus 4 is divided by x plus 2. First, we identify our polynomial, p of x, and our divisor. The divisor is x plus 2, which we can write as x minus negative 2. So our value of k is negative 2. According to the remainder theorem, the remainder will be p of negative 2. We substitute negative 2 into the polynomial. This gives us negative 2 to the power of 4 minus 3 times negative 2 cubed plus negative 2 minus 4. Calculating this, we get 16 plus 24 minus 2 minus 4, which equals 34. Therefore, the remainder is 34. We have now successfully applied the remainder theorem to find a remainder without performing long division. This is a powerful and efficient technique. Now let's tackle a more complex problem involving unknown coefficients. This is a common type of question in IB exams. The problem states that when the polynomial x cubed plus 4x squared plus ax plus b is divided by x minus 2, the remainder is 20. And when it's divided by x plus 5, the remainder is 6. We need to find the values of the constants a and b. Let's define our polynomial as p of x. We have two pieces of information, which will allow us to create a system of two equations with two unknowns, a and b. First, let's use the information about the divisor x minus 2. The remainder theorem tells us that p of 2 must equal the remainder, which is 20. Substituting 2 into our polynomial, we get 2 cubed plus 4 times 2 squared plus a times 2 plus b equals 20. Simplifying this gives us 8 plus 16 plus 2a plus b equals 20. Combining the constants, we get our first equation. 2a plus b equals negative 4. Now, let's use the second piece of information, the divisor x plus 5. The remainder theorem tells us that p of negative 5 must equal the remainder, which is 6. Substituting negative 5 into our polynomial, we get negative 5 cubed plus 4 times negative 5 squared plus a times negative 5 plus b equals 6. Simplifying this gives us negative 125 plus 100 minus 5a plus b equals 6. Combining the constants, we get our second equation. Negative 5a plus b equals 31. We now have a system of two linear equations. Equation 1 is 2a plus b equals negative 4. Equation 2 is negative 5. A plus b equals 31. We can solve this using the elimination method. If we subtract equation 2 from equation 1, thus, b terms will cancel out. Subtracting the equations, we get 2a minus negative 5a, which is 7a, and negative 4 minus 31, which is negative 35. So, 7a equals negative 35. Dividing by 7, we find that a equals negative 5. Now we substitute this value of a back into either equation to find b. Let's use equation 1. Substituting a equals negative 5 into 2a plus b equals negative 4, we get 2 times negative 5 plus b equals negative 4. This simplifies to negative 10 plus b equals negative 4. Adding 10 to both sides, we find that b equals 6. So we have found our constants. A equals negative 5 and b equals 6. This example demonstrates how the remainder theorem can be used to solve for unknown coefficients in a polynomial. Next, we will explore the factor theorem, which is a direct consequence of the remainder theorem. The factor theorem states that for a polynomial p of x, x minus k is a factor if and only if p of k equals 0. Let's break down what this means. The phrase, if and only if, indicates a two-way relationship. First, if x minus k is a factor of p of x, it means that when you divide p of x by x minus k, the remainder is 0. By the remainder theorem, this remainder is p of k. Therefore, p of k must be 0. Second, if p of k equals 0, the remainder theorem tells us that the remainder when dividing p of x by x minus k is 0. A 0 remainder means that x minus k divides p of x perfectly, making it a factor. In essence, finding a 0 of a polynomial is equivalent to finding a linear factor. Let's work through an example. We need to find the value of k such that x minus 2 is a factor of the polynomial x cubed plus kx squared minus 3x plus 6. Let's call our polynomial p of x. Since x minus 2 is a factor, the factor theorem tells us that p of 2 must be equal to 0. We substitute 2 into the polynomial. 2 cubed plus k times 2 squared minus 3 times 2 plus 6 equals 0. Simplifying this, we get 8 plus 4k minus 6 plus 6 equals 0. The negative 6 and positive 6 cancel out, leaving us with 8 plus 4k equals 0. Solving for k, we subtract 8 from both sides to get 4k equals negative 8, and then divide by 4 to find that k equals negative 2. So we have found the value of k. The polynomial is now fully defined. The polynomial is x cubed minus 2x squared minus 3x plus 6. We know that x minus 2 is a factor. The problem also asks us to fully factorize this polynomial. To do this, we need to find the other factors. We can use polynomial division for this. We will divide p of x by x minus 2. Using synthetic division, we set up the coefficients of the polynomial and the root, 2. We bring down the first coefficient, 1. We multiply 1 by 2 to get 2, and add it to the next coefficient, negative 2, to get 0. We multiply 0 by 2 to get 0, and add it to negative 3 to get negative 3. We multiply negative 3 by 2 to get negative 6, and add it to 6 to get 0. The final 0 confirms that the remainder is indeed 0. The resulting coefficients, 1, 0, and negative 3, represent the quotient. Since we started with a cubic polynomial and divided by a linear factor, the quotient is a quadratic, x squared minus 3. So we can write p of x as the product of the divisor and the quotient, x minus 2 times x squared minus 3. We can factorize this further using the difference of squares formula. A squared minus b squared equals a minus b times a plus b. X squared minus 3 can be written as x squared minus the square root of 3 squared. This factors into x minus the square root of 3 times x plus the square root of 3. Therefore, the fully factorized form of the polynomial is x minus 2 times x minus the square root of 3 times x plus the square root of 3. This example shows how the factor theorem is a powerful tool for finding factors and simplifying polynomials. Let's look at another example that combines the remainder and factor theorems. This problem involves a polynomial with two unknown coefficients and two conditions. We are given the polynomial p of x equals 2x cubed plus ax squared plus bx plus 5. We know that x minus 1 and x plus 5 are both factors. Our goal is to find the values of a and b. Since x minus 1 is a factor, the factor theorem tells us that p of 1 must be 0. Substituting 1 into the polynomial, we get 2 times 1 cubed plus a times 1 squared plus b times 1 plus 5 equals 0. This simplifies to 2 plus a plus b plus 5 equals 0. Combining the constants, we get our first equation. A plus b equals negative 7. Now let's use the second factor, x plus 5. Since x plus 5 is a factor, p of negative 5 must be 0. Substituting negative 5 into the polynomial, we get 2 times negative 5 cubed plus a times negative 5 squared plus b times negative 5 plus 5 equals 0. This simplifies to 2 times negative 125, which is negative 250, plus 25a minus 5b plus 5 equals 0. Combining the constants, we get our second equation. 25a minus 5b equals 245. We now have a system of two linear equations. Equation 1 is a plus b equals negative 7. Equation 2 is 25. A minus 5b equals 245. We can solve this using the elimination method. Let's multiply equation 1 by 5 to make the, b, coefficients opposites. Multiplying equation 1 by 5 gives us 5a plus 5b equals negative 35. Now we add this new equation 3 to equation 2. Adding the equations, we get 25a plus 5a, which is 30a. The b terms cancel. And 245 plus negative 35 is 210. So 30a equals 210. Dividing by 30, we find that a equals 7. Finally, we substitute a equals 7 back into equation 1 to find b. 7 plus b equals negative 7. Subtracting 7 from both sides, we get b equals negative 14. So, the constants are a equals 7 and b equals negative 14. This problem demonstrates how to set up and solve a system of equations using the factor theorem, a crucial skill for IBHL. We now move to the fundamental theorem of algebra, which is a cornerstone of polynomial theory. The fundamental theorem of algebra states that if p of x is a polynomial of degree n, where n is greater than or equal to 1, then p of x has exactly n zeros in the complex number system. This means that a polynomial of degree 3 will have 3 zeros, a polynomial of degree 4 will have 4 zeros, and so on. These zeros can be real or complex, and they can be repeated. A key consequence of this theorem for polynomials with real coefficients is the conjugate root theorem. The conjugate root theorem states that if a polynomial p of x has real coefficients, and if a plus bi is a 0, then its complex conjugate, a minus bi, must also be a 0. This theorem is incredibly useful because it guarantees that complex zeros always come in pairs. This means that a polynomial with real coefficients can never have an odd number of complex zeros. Let's apply this to an example. Suppose negative 3 plus I is a 0 of the polynomial p of x equals ax cubed plus 9x squared plus ax minus 30, where a is a real number. We need to find a and all the zeros. First, let's use the conjugate root theorem. Since the coefficients of p of x are real and negative 3 plus I is a 0, its conjugate, negative 3 minus I, must also be a 0. Now we have two zeros. We can use them to find a quadratic factor of p of x. A quadratic with these two zeros can be written as x squared minus the sum of the zeros times x plus the product of the zeros. The sum of the zeros is negative 3 plus I plus negative 3 minus I, which equals negative 6. The product is negative 3 plus I times negative 3 minus I, which is 9 minus I squared. Since I squared is negative 1, the product is 9 plus 1, which is 10. So, the quadratic factor is x squared minus negative 6x plus 10, which simplifies to x squared plus 6x plus 10. We know that p of x is a cubic polynomial. If we divide it by this quadratic factor, we must get a linear factor. Let's call this linear factor ax plus c. So, p of x equals the quadratic factor times the linear factor ax plus c. We can find a and c by expanding the right side and equating coefficients with the original polynomial. Expanding the right side gives ax cubed plus 6ax squared plus 10ax plus cx squared plus 6cx plus 10c. Grouping terms by power of x, we get ax cubed plus the quantity 6a plus c times x squared plus the quantity 10a plus 6c times x plus 10c. Now we compare this to the original polynomial p of x equals ax cubed plus 9x squared plus ax minus 30. By comparing the constant terms, we see that 10c must equal negative 30, which means c equals negative 3. Now we can find a by equating the coefficients of x squared. The coefficient of x squared is 6a plus c. This must equal 9. Substituting c equals negative 3, we get 6a minus 3 equals 9. Adding 3 to both sides gives 6a equals 12, so a equals 2. We have found a equals 2 and c equals negative 3. Let's check this with the x coefficients. The coefficient of x is 10a plus 6c. Substituting our values, we get 10 times 2 plus 6 times negative 3, which is 20 minus 18, which equals 2. The original coefficient of x was a, which we found to be 2. The values are consistent. So a equals 2, and the linear factor is ax plus c, which is 2x minus 3. The zeros of the polynomial are the zeros of the quadratic factor and the linear factor. The zeros of x squared plus 6x plus 10 are negative 3 plus I and negative 3 minus I. The zero of 2x minus 3 is 3 over 2. These are the three zeros of the cubic polynomial. Let's work through another example involving complex zeros, this time with a purely imaginary zero. We are given the polynomial p of x equals ax cubed plus the quantity a plus 1 times x squared plus 10x plus 15, where a is a real number. We are told that one zero is purely imaginary. We need to find a and all the zeros. A purely imaginary number is of the form bi, where b is a non-zero real number. Let's call this 0 bi. Since the coefficients of p of x are real, the conjugate root theorem tells us that its conjugate, negative bi, must also be a 0. Now we find the quadratic factor corresponding to these two zeros. The sum of the zeros is bi plus negative bi, which is 0. The product is bi times negative bi, which is negative b squared, I squared. Since I squared is negative 1, the product is b squared. The quadratic factor is x squared minus 0x plus b squared, which is simply x squared plus b squared. As before, we can write p of x as the product of this quadratic factor and a linear factor. Let's call the linear factor c, x plus d. So p of x equals x squared plus b squared times c, x plus d. We can find c and d by comparing the coefficients of the expanded form with the original polynomial. Expanding the right side gives cx cubed plus dx squared plus cb squared x plus db squared. Comparing this to p of x equals ax cubed plus the quantity a plus 1 times x squared plus 10x plus 15. By comparing the coefficients of x cubed, we see that c must equal a. By comparing the constant terms, we see that d b squared must equal 15, so d equals 15 over b squared. Now we have expressions for c and d in terms of a and b. Let's use the remaining coefficients to form equations. Equating the coefficients of x squared, we get d equals a plus 1. Substituting our expression for d, we get 15 over b squared equals a plus 1. This is our first equation. Equating the coefficients of x, we get c b squared equals 10. Substituting c equals a, we get ab squared equals 10. This is our second equation. We now have a system of two equations with two unknowns, a and b. Equation 1 is 15 over b squared equals a plus 1. Equation 2 is ab squared equals 10. From equation 2, we can see that b squared equals 10 over a. Let's substitute this into equation 1. Substituting b squared equals 10 over a into equation 1, we get 15 divided by 10 over a equals a plus 1. This simplifies to 15, a over 10 equals a plus 1. Multiplying both sides by 10 gives 15a equals 10a plus 10. Subtracting 10a from both sides gives 5a equals 10, so a equals 2. We have found a equals 2. Now we can find b squared using equation 2. 2 times b squared equals 10, so b squared equals 5. This means b equals plus or minus the square root of 5. We have found a equals 2. The purely imaginary zeros are plus or minus I times the square root of 5. The linear factor was c x plus d, which is ax plus 15 over b squared. Substituting our values, the linear factor is 2x plus 15 over 5, which is 2x plus 3. The zero of this factor is negative 3 over 2. Therefore, the zeros of the polynomial are I times the square root of 5, negative I times the square root of 5, and negative 3 over 2. This example highlights the importance of the conjugate root theorem when dealing with purely imaginary zeros. Let's start by writing a simple equation. Now let's highlight the variable x. And now, let's clear the content. Thanks for watching. Let's quickly recap what we've learned today. We started with the remainder theorem, which allows us to find the remainder of a polynomial division by evaluating the polynomial at a specific point. We then saw how the factor theorem is a special case of the remainder theorem, where a zero remainder indicates a factor. Finally, we explored the fundamental theorem of algebra and the conjugate root theorem, which are essential for understanding the nature and number of zeros of a polynomial, especially when dealing with complex numbers. These theorems are powerful tools for solving problems involving polynomials, finding unknown coefficients, and factorizing expressions. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Find the remainder when 3x cubed minus 2x squared plus 5x minus 1 is divided by x plus 2. Question 2. Given that x minus 3 is a factor of x cubed plus ax squared minus 11x plus 6, find the value of a. Question 3. When the polynomial p of x equals x cubed plus ax squared plus b x minus 10 is divided by x minus 1, the remainder is negative 6. When divided by x plus 2, the remainder is negative 24. Find the values of a and b. Question 4. A polynomial p of x has real coefficients. If 2 plus I is a 0, and p of 1 equals 10, find the polynomial p of x. Question 5. The polynomial p of x equals x cubed plus ax squared plus b, x plus c, has zeros at x equals 1 and x equals 2 plus I. Find a, b, and c. Welcome back. Let's go through the solutions to the practice questions. For question 1, we use the remainder theorem. The divisor is x plus 2, so k is negative 2. The remainder is p of negative 2, which is 3 times negative 2 cubed minus 2 times negative 2 squared plus 5 times negative 2 minus 1. This simplifies to negative 24 minus 8 minus 10 minus 1, which equals negative 43. For question 2, we use the factor theorem. Since x minus 3 is a factor, p of 3 must be 0. Substituting 3 into the polynomial, we get 3 cubed plus a times 3 squared minus 11 times 3 plus 6 equals 0. This simplifies to 27 plus 9, a minus 33, plus 6 equals 0. Combining terms, we get 9a equals 0, so a equals 0. For question 3, we set up a system of equations. P of 1 equals negative 6 gives us 1 plus a plus b minus 10 equals negative 6, which simplifies to a plus b equals 3. P of negative 2 equals negative 24 gives us negative 8 plus 4a minus 2 b minus 10 equals negative 24, which simplifies to 4a minus 2b equals negative 6. Solving this system gives a equals 0 and b equals 3. For question 4, since 2 plus i's, a's 0, its conjugate 2 minus I is also a 0. The quadratic factor is x squared minus the sum, 4x, plus the product, 5. So p of x equals c times this quadratic. Using p of 1 equals 10, we find c equals 2. The polynomial is 2x squared minus 8x plus 10. For question 5, the zeros are 1, 2 plus I, and its conjugate 2 minus I. The polynomial is the product of the three linear factors. Expanding this gives x cubed minus 5, x squared, plus 9x minus 5. Comparing coefficients, we find a equals negative 5, b equals 9, and c equals negative 5. I hope this video has provided a clear and rigorous explanation of the remainder theorem, factor theorem, and the fundamental theorem of algebra. Mastering these concepts is essential for success in IB Mathematics Day AHL. Thank you for watching.